Fantastic. OK. Who's excited about data stores? All right, you're in the right room. We're going to talk a lot about data stores today. My name is Joey, as you just heard, and I work at Yelp, which is a company that connects people with great local businesses. It's kind of our business model. We have a ton of data. We have 92 million unique monthly visitors on mobile devices alone. We have 108 million reviews contributed since conception. Approximately 72% of all of our searches come from mobile, and we've launched in about 32 countries across the world. So we have a lot of data, and with that comes some pretty interesting data tiers. But what about me? Because why should you trust me? Well, maybe you shouldn't. But if you do, I hope it's because I've worked with these systems for many years. I've actually personally worked on taking Yelp from a monolithic MySQL data tier to a polyglot, multiple different data stores, fine-tuned data tier that consists things like Cassandra and Elasticsearch. Along the way, I've been an avid engineering tech blogger on our engineering blog. I've written about Elasticsearch, about Cassandra, and about just generally how to do microservices. So this talk is going to be split into 4 parts. I'm going to start with why would you ever want more than one data store? One's hard enough, right? Why would you want more than one? Then I'm going to talk about, given that you want more than one, what's out there? What's out there in open source? What can we use? Then I'm going to move to kind of more technical part of the talk. So the first half will be a little bit more high level, a little bit more exploratory, and then we'll shift into how do I actually make this happen in production? And that's going to be then followed by the realities of making this choice. So if you go down the polyglot data store route, what realities are you going to have to contend with, and how are you going to have to think about your data? All right, so let's get started. Why do I want more than one data store? Well, how many of you guys have an application that looks something like this? You've got presentation, logic, and data. Show of hands. A fair number of people. It's a pretty common architecture. But nobody does just this anymore, right? Now you've got 22 different front-end technologies, React, Angular, you've got Android, iOS, IE6 is a front-end technology all by itself. Then in your logic tier, you're microservicing it up, right? You're DevOpsing it up. You've got Node.js, Go, Python, Java, services, they're all talking to each other. But what about your data tier? What about that last one? Well, we just throw MySQL there and we're done, right? MySQL just scales infinitely and works perfectly. And the reality is that this actually does work for a while. I've seen shops push Postgres and MySQL farther than I ever thought you could. But sometimes it stops working. And at Yelp, it stopped working when we started doing something crazy like this, where we ended up with kind of like lots of different verticals that were all optimized. So for example, your search vertical isn't going to use MySQL. That doesn't make sense. We're going to use a data store which is optimized for search. If you are handling people's money, then you don't want to use something like maybe Elasticsearch to store your data. You're going to have a bad day. So this kind of like hyper-optimization of each of your verticals is one reason why you might end up going polyglot. All right, so let's say that you say, hey, that architecture looked a little bit like mine. I've got services talk to all different services. They've got different data stores. How am I going to do this? Well, you have a choice here. You can either invest engineering effort in taking your existing, like essentially monolithic data store and trying to shard it and scale it. And some companies have very successfully done this. Like if you've got Facebook's engineering org, go ahead and do this. However, at Yelp, we don't have Facebook's engineering org. We don't have thousands and thousands of engineers. So we instead reached into open source, and we looked at the great data stores that are coming out of the NoSQL and NewSQL movements in the past decade. And you can very successfully do this. But if you do, what's out there? What options do you have? Well, sometimes, unfortunately, many options. Right? Who's looked at data stores and seen something like this and been like, whoa, I can't even begin to know what's going on here. And to be honest, I haven't worked with all of these. I don't think it's possible to work with all of these. I have worked with many of them. And I'm going to talk in this talk a little bit about how you can kind of navigate this landscape. But I do want to take a second here and just kind of repeat something that I thought was interesting in one of the keynotes, which is open source has won, right? 12 out of 20 of the top data stores, according to this random dbengines.com website, which ranks data stores, I don't exactly know how, but it looks about right. 12 out of 20 of the top ones are open source. That's awesome, right? Yelp uses 7 out of 8 of the top open source data stores in production. That's, I think, a fantastic success story for open source. But how about navigating it? How about picking between all of these options? Well, before I get into that, I just want to warn you guys. I'm going to say some things. You might not agree with me. That's okay. These data stores are changing constantly. You have different production infrastructures, you have different business needs, and different experiences. So try to look at what I'm about to say more of as a process for how to evaluate data stores, rather than necessarily like this data store is better than this data store. And that's also true because data stores are constantly changing. And this talk is not a substitute for keeping track of how they're changing. So the first thing I want to do is I want to kind of roughly group the data stores to help us kind of get an idea of what we're going to talk about. So the grouping that we all might be familiar with is the relational grouping. Things like MySQL, Postgres. These guys are kind of the stalwart data stores in the open source world. They've been around for decades. But recently, we've also seen a fairly like resurgence in the document store world, and these are kind of like somewhat tied back to object data stores in the 1970s. In particular, MongoDB has just become absolutely wildly popular in the Node.js community. There are other options like Rethink and CouchDB, but they're a little less popular. Then you also have this idea of key value stores, which I'll touch on in a bit. But these are things like Cassandra, HBase, Memcache, Redis, Riak. And in a totally different world, you've got search engines, the whole Lucene family. So Lucene was kind of like Lucene and Sphinx were the open source search engines 5-10 years ago. And recently, Solr and Elasticsearch have really kind of come on the scene, which are both based on Lucene. But you also have kind of a little bit more esoteric or special purpose data stores, things like configuration services like Zookeeper, Consul, etcd. And you're starting to see things like specifically for streaming data like Kafka or Apache Bookkeeper. But it doesn't stop there. You've got an open source data store for a time series database, InfluxDB. You've got Riak time series open source. And pretty much anything, any application you can think about, there's a data store that's built for that. Do you need globally transactional SQL type reads? Well, Cockroach is trying to do that. Do you have graph database needs? Neo4j is trying to do that. Do you have analytics? Hypertable is trying to do that. In the interest of time, we're not going to cover all of these. I can't possibly cover every data store that exists, but I will try to cover these 5 main areas. And the reason there's a cat here is because when I was giving this talk, my coworker was like, "You need more cats." And I was like, "Okay." So here's a cat looking at our data stores. So let's get started. Let's start with the relational landscape. There are 2 big players here, MySQL and Postgres, and they're really amazing. They're the stalwarts. They're the first stop. These have worked. They've worked for decades. And I think that they work so well because they're based on, like, they're one of the few data stores that are actually based on academic research. So in the 1970s, there was a series of papers about the relational model for shared data banks. And ever since the 70s, we've been using these guys in production. So they're very, well, not these particular data stores, but they're very old and very, as a result, reliable. The tooling is great. These things are solid. But one thing we've started noticing over the past couple of years is that they have this thing called object relational impedance mismatch. Who knows what that is? A couple people, yeah. It's this notion that your data model is relational, but your code is object-oriented. And there's this kind of like mismatch between how you think about them. So to kind of deal with those, that impedance mismatch, document stores came out maybe 5-10 years ago, trying to help a little bit with that. So things like Mongo, CouchDB, Rethink. I'm sorry, Rethink. Rethink was a great data store. But these data stores remove that impedance mismatch. You just write your code and your data looks exactly the same. But this obviously has a trade-off, namely that I haven't seen one of these data stores, with the exception of maybe Rethink, which does correctness right. And what I mean by that is that you might not be able to read your writes, you might not be able to do transactions, and it can be really hard to kind of reason about how these systems operate at scale. However, they are pretty popular and they're really intuitive. But speaking of intuitive, there's a whole class of data store that haven't come out recently. They've been around forever, which is also very intuitive. And those are key value stores in memory. This is basically saying, hey, I got my hash map in my programming language. I'm going to put it on multiple machines, and it's going to be so fast. And that's really the big pro of these data stores. They are amazingly fast. I have never seen another data store compete with Redis or Memcache in terms of ability to actually do operations per second. It's crazy. However, they have and that's because memory is like 10 to 100 to 1,000 times faster than disks, depending on which kinds of disks you have. But there's a trade-off. And one thing I've noticed, at least at Yelp, is that sometimes we put things that really shouldn't be in memcache in memcache. Anybody else do this? Yeah, one or two? Okay, you feel my pain. And this has some natural scaling limits because your data has to fit in RAM, and you might lose it if you lose the box. Asterisk Redis does persistence, so Redis is a little bit more appropriate as a choice as a primary data store than memcache is. But still, I would rather pick a durable key value store if I actually care about my data. And these guys all came out of a series of papers released by Google and Amazon, the Dynamo paper and the Bigtable paper. And open source kind of was like, hey, this idea is pretty cool. Let's do this too. And luckily, we've got a bunch of good options. We've got Apache HBase, Cassandra, and these are awesome because they solve that write scalability problem that was so problematic for MySQL data stores. And this is because of the data structure they use under the hood. So they use something called log structure merge trees or SS tables, sorted string tables. And these data structures are very optimized for write-heavy workloads. However, they have a trade-off, which is that the latency of reading from them can be worse. So you've got that write scalability, and in terms of operations per second, you've got read scalability with these data stores. So you can do a lot of throughput both on write and read. But when you try to read your data, especially a lot of it, it can be a little slow. So if you're trying to use these guys in an interactive request-response workload, you just have to be cognizant that you're not going to get 250 microsecond reads out of them like you might be getting out of MySQL. But also, I think one of the biggest problems with these data stores is that they require engineers to kind of flip the model. So with MySQL or traditional RDBMSs, you model your data. With Cassandra or HBase, you model your queries. You have to kind of think ahead of time, what questions am I going to ask? And then you use that to create your data model. So this can be very unintuitive for developers who maybe aren't used to thinking that way. But luckily, there are other data stores where querying is very easy, and they're called search engines. Search engines are wonderful because you can ask them basically any question that you ever want. You can ask real-time queries, you can ask analytics queries, and that's because they're based on a totally different data structure than the ones that we saw before. These guys are based on an inverted index, which means that instead of your traditional database where you map primary keys to data, with inverted indices, you map data to lists of primary keys. And this allows you to do things like full table scans extremely quickly. They're really nice for searching and for complex querying. But again, these data stores have trade-offs, in particular around consistency. You're going to have to figure out how to keep these data stores consistent with a source of truth because search engines tend to not have the best durability guarantees. Also, I just wanted to mention here, reading your writes, which we all kind of take for granted. So like I write data to my database and then I read from it. This only got added to search engines maybe 2-3 years ago. Elasticsearch was kind of the first search engine I'm aware of which actually had the ability to write data and then turn back and read it. And this is, I think, kind of an ode to their history of not being terribly consistent. But consistency is nice, right? We've heard that consistency is good. Luckily, there are data stores that allow you to get consistency as well. When you're running a few thousand nodes, you're going to have to coordinate actions between them. And that's where these guys come in. In fact, I almost consider things like Zookeeper and Consul and etcd, I consider these foundational data stores. They're used by other data stores to solve the hard problems, which is kind of interesting given how many hard problems data stores solve. And that's because nobody really wants to solve distributed consensus. It's really, really hard to do correctly. So that's kind of the nice thing about these data stores is your product, your application, or your data store doesn't have to solve them. The problem, the trade-off, is that you've gone very far down the cap trade-off. So you've gone very far down consistency to the point where you are sacrificing availability. And I can't tell you how many times maybe I've personally put Zookeeper in the data plane of our application and had a bad day. Like, that's not where this data store belongs. This data store belongs in your control plane, kind of helping to coordinate everything else. All right, so that was kind of a whirlwind tour through the landscape. Let's get to actually some examples of picking a data store. And to do that, I want to give you guys my 4-step process for picking a data store. Step 1, does the data store satisfy the business requirement? And I think this is really important because at least at my company, we have a lot of things that are like, oh, I read about this thing on Hacker News, maybe we should deploy it on production. And you first have to ask, whenever somebody comes to you, I want to deploy a new data store, is it solving a business requirement? Step 2, because we're in open source world, we have to consider the community. There isn't necessarily a company that's guarding this data store. Thankfully, often there is, but you have to think about is that community solid? And I think that people who used Rethink are kind of going through this process right now. They maybe didn't think enough about step 2. Step 3, does it plug into your stack? And this is where Yelp might make weird choices from your guys' perspectives, because our stack is kind of weird. I'm sure your guys' stack are a little weird too. All of our stacks are a little weird. But data stores are going to work more natively with certain languages. For example, like Java is a very well-supported language across all your data stores. Python, maybe a little less. Fourth question, how badly broken is it? So software is all broken. Data stores are software, ergo, data stores are also going to be broken. But the question is not, are they broken? The question is, how broken are they? And do people know about how to work around those issues? So for example, MySQL has a ton of issues, but we know about them. And so it's easy for the community to kind of work around them and kind of know where those boundaries lie. So these 4 questions. And before we get into picking data stores, we have to know Yelp stack. So Yelp is a massive Python shop. That graph is showing our lines of code in all of our apps. That's 3 million lines of Python. We have a couple 100,000 lines of Java as well. And both of those applications, they run on both our data centers and in the cloud. So we do hybrid cloud, and we monitor them all with Sensu. And we have about 300 developers, 300 to 400 developers. What does this mean? Well, this means that when we're picking data stores, we have to take this into account. We have to think about Python compatibility, about libraries, but we also need to think about things like monitoring APIs. Is the data store going to expose an API that we can use to monitor? And then lastly, because we have all these developers, we're going to need good tools and documentation. All right. So let's tell a little bit of a story here. Let's take a trip back in time. 2011, Yelp has 1 data center, about 80 developers, and 1 server. We have a monolith. It's a monolith. And we're basically running a LAMP stack with the addition of Lucene, and we'd used Scribe from Facebook for logging. 2012 comes along, and we add another data center, and we start adding more developers, and we hear about this service thing, which now we call microservices, but back then we just call it services. And we started running into some issues. The first issue we ran into was I kept accidentally double flipping the entire search cluster and bringing down the website. And the reason why that happened is because we had automatic restarts which were happening, and then I would go and restart to pick up a code deploy, and then those 2 scripts wouldn't be mutually exclusive. So we needed some way to ensure that our automation didn't kill the website, and that's what distributed configuration stores are for. Also, with those additional services, we started thinking about, hey, maybe we need a service registry. Maybe we need some way to know where these services are. We can't just have Joey over there writing this down in a YAML file forever, right? So we needed a registry. We needed distributed locks. And we looked at the open source ecosystem, and Zookeeper was there. Zookeeper was the only option in 2012. It was funny because when I was going through this slide deck, I was like, wait a minute, why didn't we use etcd or console? And the answer is they didn't exist yet. So this is often a way that you're going to make a decision because there's only one choice. However, we have had some regrets. So for example, on the plus side, Zookeeper works really well. On the regret side, 4-letter words piped over echo to a netcat, like that's not an API, right? Like I think console and etcd are doing a much better job of having proper APIs. At the same time, with those additional developers, we started wanting to build more features. So Yelp connects people with great local businesses. Well, that's a search problem. And we wanted developers to be able to write search applications. But the problem was that our stack was based on Lucene, but our developers all knew Python. That doesn't work so well, because you have to write Java to be able to write search applications in Lucene. So we looked around, and Elasticsearch was in version 0.12. And we deployed that on production. Yeah, no, OK. Anyone else who's run Elasticsearch 0.12 in production, you know my pain. And that was kind of the downside, was that we were very early adopters and we got bit by a lot of issues. However, it enabled a ton of innovation. So here's a screenshot of our homepage. And all those green boxes are powered by Elasticsearch. These are features which were able to exist because we added that data store. Things like recommendations of where people should write reviews based on where they've been. Things like searching over your talks, your talk posts and your list posts. And basically any feature on Yelp now can support search pretty easily because we have that easy API that's easy for developers to use. On the search page, it's the same story. Like, all that real estate is powered by Elasticsearch under the hood. Things like snippeted reviews, where we can summarize reviews into small snippets that are actually digestible by people. That's all powered by Elasticsearch. So I think that this is kind of a story of, yes, it was hard to be an early adopter, but that data store allowed our company to deliver business value. And I think that's really the key. So 2012 came around, we added Zookeeper to help with me bringing down the search cluster, and we added Elasticsearch to enable all these cool feature developments. What about 2013? Well, 2013, Scribe's kind of abandoned. It's kind of a bummer. That sometimes happens with open source projects, and you do have to be aware of that. So we start thinking ahead and are like, hey, what else is out there? Luckily, Kafka came on the scene, and Kafka was a really good replacement for us for Scribe. I'm not going to go into too many details in the interest of time on that. So you can kind of see that we're sort of doing that SOA thing now, right? We've got 30 services, 4 data centers, 200 developers, and then 2014 happens, and we scale even further. And then it just starts burning. 2014 was a bad year for SREs. And the reason for that was because we were trying to push data stores in directions that they really couldn't go. So I want to give a concrete example. Here we have a feature where we show business owners on Yelp interactions that users have had with their business. And this sounds like a reasonable feature. The problem is that this is a massively write-heavy workload, right? Every interaction anybody ever does with the website gets written to a MySQL table. Well, it turns out, very hard for MySQL. At one point, we were using 80% of our replication capacity to slaves just to satisfy this one feature, right? It was kind of crazy. But also, occasionally, it would bump over that 100%, and our masters and slaves would start lagging, and, well, MySQL would catch fire. So this was kind of unfortunate. But at the same time, we were having another problem, which was we had all those data centers, and we had these little memcache instances that weren't replicated. And as it happens, sometimes a data center blows up, and that's a bummer. But no problem, we just fail over. All right, who can guess what happened next? This guy blew up too. And the reason why is because the cache was cold. When you don't have replicated caches and you're working with massive amounts of traffic, you can very easily blow up your databases or other things if your caches are cold in your failover regions. So we kind of had these problems, and we were thinking, is there any way we can solve these with open source data stores? Luckily, durable key value stores solve both of these problems pretty fantastically. In the case of the first problem, they're able to take massive amounts of reads. In fact, we can scale to as many reads as we want. That's awesome. They also do the reads fast enough for our product, so that's also good. But the thing that I think was really the deciding factor that made us go with Cassandra here was that we could do globally available caches as well. We could do globally multi-master writes as well. And we do have some regrets, like we've had some issues with the Cassandra Python driver, but I do think that comparatively this was a pretty good choice. It's worked out pretty well for us. So you can kind of see here that each one of these data stores was added in response to business pressure. We had business needs, and I really think that that's how you build powerful data tiers, is by adding data stores sensibly in response to business needs. And look, you've got a powerful data tier here. You want search? You got it. You want relational databases? You got it. You want high volume read-write? You got it. So I think that this is kind of gives you guys an illustration of how that happened. Awesome. So now let's dive into kind of like the technical meat of the talk. How are we actually going to build this? Well, because this is OSCON, we're going to do it with DevOps, folks. We're going to show you how to deploy, configure, monitor, discover, and what tooling we need to build. All right, so the first step we got to do is actually get machines running. And at Yelp, we use this great open source tool called Terraform, which allows us to spin up an Amazon autoscaling group in that many lines of code. This, to me, is infrastructure as code. It's super cool. The trade-off is a little unstable. I can tell you that we've had at least one postmortem that was entitled Terraform, how we deleted everything. So you have to be careful. But it's a very powerful tool, and it allows you to, in 42 lines, make a Cassandra cluster. And it's really just these last 4 lines here, this little thing that's telling the ASG, when you launch an instance, tag it as a Cassandra node. And that's where the magic starts, that little 3 lines at the end. That's what informs Puppet ENC. So Puppet and Chef, if you use Chef, both have the ability to take external information and use that to apply a certain configuration profile. So in our case, we use this to apply cluster modules for various data stores. And I just want to call out that these modules are doing more than just configuring Elasticsearch or Cassandra. The open source modules do that fine. What the cluster modules do is they bring it up a level of abstraction and allow you to think about it in terms of the cluster rather than an instance. So your open source modules in both Puppet and Chef are going to be focused on an instance, but we care about the cluster. So how does that actually work? Well, the way we do that is with hierarchical config. So here's an example of a Cassandra configuration file. And if any of you guys have ever worked with Cassandra, there's a ton of tunables, right? There are certain things that you have to change per version of the data store. There are certain things that you have to change per cluster. There are certain things that you might even have to tune per node. And functions help a little bit in terms of, for example, like not hand tuning things that thread pools that should be the number of CPUs. But hierarchical config is better. And I want to show you how. So at Yelp, we use these Puppet module data hierarchies. And what they allow you to do is instead of using your overall Puppet repositories hierarchy, which is usually things like node, availability zone, region, superregion, which we don't really care about for data stores, they allow you to define a custom hierarchy. And in our case, we care most about what cluster is it in, because specific cluster config overrides anything else, followed by which version of the data store is it running. Cassandra 2.2 is configured differently from Cassandra 3. And finally, there's a default where we just set good defaults. So I think this is super powerful, because it's allowed us to do something like this, where when a developer wants a cluster, all we have to do is add a little file in the clusters directory. Add a single YAML file. It usually contains almost nothing. And then it automatically picks up the config from all the other versions. So you can run multiple versions of the data store, you have good defaults, and you can configure it per cluster. And to kind of give you an example of what that looks like in production, almost all of the config that we specify for like a Cassandra.yaml file goes in the version-specific config. And that's because that's where things usually change. When you upgrade data stores, certain configuration variables are no longer valid, some of them are. So that's where most of the config goes. The base config has almost nothing in it. And the clusters config only has things that that particular cluster of Elasticsearch, Cassandra, Zookeeper, Kafka need. Typically, this is empty. I've shown an example here where we've enabled client-side encryption for one cluster. But like that's all that we had to do to enable client-side encryption for one cluster. So I think it's pretty awesome. Puppet module data has been huge in allowing us to iterate on these kind of multi-cluster deployments. And to kind of give you context, we're running about 200 to 300 clusters of data stores right now. And we are able to configure them all very fine-tuned because of this. But what about monitoring? Monitoring is important, right? It's not done until it's monitored. And I guess the one takeaway that I want to say here is treat your databases like services. So just like you don't monitor individual Docker containers, you monitor health of applications, do the same thing for your data store. Page people when the overall data store is about to go down, not when a single node fails. This was a huge culture change for Yelp because we were kind of used to like MySQL where like we really care about every node. But then when you start using Cassandra, Elasticsearch, these distributed first data stores, you don't have to do that. And in fact, your developers are going to get really unhappy with you if you page them because a single node failed and everything's still fine. Some data stores are easy to do this with. Elasticsearch comes out of the box with good monitoring APIs. Cassandra doesn't. And I wrote a blog post about how we kind of jury-rig our way in to be able to monitor things like Cassandra at scale. All right, but we're not done until your developers can actually find your data store. And data stores, sorry to break it to you, data stores don't register in your service registry, right? Like they're written in some other language, maybe they're written in Erlang. They're not going to register in your registry. So what we do is we use a sidecar pattern. And this is actually the same thing that we do for services at Yelp. Again, kind of repeating the theme of treat your data stores like your services. So we have this little sidecar called Nerve, which is able to health check the data store and then register it in a registry. And then Synapse, on the other end, pulls from the registry and configures a local routing component on all your clients. In this case, it's HA proxy. The astute among you might mention, hey guys, HA proxy really not a good thing for data store clients to talk through. And you'd be right, it's really not. So one of the first things that I contributed upstream to SmartStack is the ability for SmartStack to write out local JSON files so that your intelligent data store clients can just read those JSON files and bootstrap directly into the cluster. But I think this is a pretty powerful system. We use this for every service. It doesn't matter if it's a data store or not. And from the developer's point of view, it's just another service. And this is what that looks like. So this is a development box, and you can see that all that a developer has to do to find a search cluster is cat this file, and poof, there are the hosts, and that's how they contact them. This is really powerful because it allows your developers to treat it just like another service. Awesome. But what about tooling? So we've kind of talked about deploying nodes, we've talked about configuring them, we've talked about getting them discovered, we've talked about monitoring them. But what about all the tooling? Because the reality is that when you choose open source, you're going to have to build some tooling. Not all the data stores come out with perfect tooling. And we've found in particular there are two classes of tooling that we always have to build. The first one being monitoring, but the first one that I'm going to talk about here is restarts. So restarting a distributed database is actually a hard problem. Doing it in a way where you don't lose availability, in a way where you can guarantee that you're not going to have availability issues for your users is tricky. So what we've done is we've built consistent restart systems for all of our data stores, Cassandra, Elasticsearch, Kafka. And the way we do that is we use Docker to build Debian packages. So we're a Debian shop, so we build Debian packages that contain a Python virtualenv using dh-virtualenv. So stay with me here. Docker builds Debian, which contains dh-virtualenv, which then contains Python code, which talks to the data store. And that sounds a little convoluted, but what it does is it allows us to use one set of tooling for essentially all the data stores. And we just have to change that little bit of functionality in the Python code that knows how to talk to a specific data store. One thing I do want to call out here is that not all your data stores are going to speak HTTP or going to speak TCP. For example, Cassandra's monitoring interface is all JMX. Good luck trying to get JMX talking to Python. It's no fun. Luckily, there's this great open source project called Jolokia, which makes this very easy. Jolokia turns any JMX endpoint into HTTP, and we're able to use the same consistent tooling for all of our data stores. But this tooling also allows some advanced things. Once you have this base ability to deploy this tooling to all of your clusters, you're now able to tackle things like automatic schema management and autoscaling. So let's dive into that. Let's see how that works. So this is a snapshot of Yelp's data store schema repository. And feature developers put the schemas that they want in this repository. And then our tooling is able to automatically apply it. And to kind of give you an example of what that looks like, developers just say, hey, I want this data store, and I want this schema applied to it. So, and this is obviously per data store. So, for example, Elasticsearch uses YAML files, Cassandra uses CQL files. But this is the kind of tooling that you can build once you have that common set of tooling that you apply to every cluster. And I just want to call it something here at the bottom, which is the owner's file. So at Yelp, our developers own their data. We take DevOps to mean DevOps, and we think that part of that is that your developers are responsible they're empowered, but they're also responsible for the data they create. But also an important piece of information here is the clusters.yaml file, which when you have hundreds of clusters, you're not going to know which index or table is supposed to be on which one. And we had this problem. It was terrible. This little piece of metadata makes your life so much better. And here's an example of those tool packages, one for Elasticsearch, one for Cassandra, implementing the apply schemata endpoint. And this allows us to just cron this up, and we can automatically apply schemata to data stores as developers ask for them. So a developer says, I want this Cassandra table, I want it on these clusters, and our tooling does the rest. And this has been really powerful for our developers because they don't have to think of that cognitive load of how am I going to apply this schema, how am I going to make sure it gets to everywhere. But it also allows you to do things like auto-scaling. So if you're on Amazon, how many of you guys have had an instance that just got killed from underneath you? Yeah, it happens a decent amount. That's cloud for you. But this is problematic for data stores because you have to be able to kind of make sure that your data is safe. And the way that we've dealt with this at Yelp is we hook into the auto-scaling lifecycle hooks that Amazon provides. And then we have these little jobs in those tools, handle AWS lifecycle events, which do things like postpone the termination event. So they basically say, hey, Amazon, give me 48 hours. I need to get all the data safely off this node. And this is all automatic, and it's all automated by our tooling. So these are the kinds of advanced things that you can build when you start thinking about cluster-wide automation. All right, so that's great. But what are the realities of making this choice? Because this sounds a little difficult. And the reality is that you're going to have to invest in some of these solutions. One thing that we invested in early on was solving this problem. So who has something like this where you have tons of data and it's getting populated by logic, it's getting populated by batches? Yeah, okay, so this is something that happens all the time at Yelp. And this is tricky because it's hard to change. Like if I want to change something from being in this Elasticsearch cluster to that Elasticsearch cluster, I can't really tell what's creating that data. Is it a batch? Is it a service? What is it? So at Yelp, what we found is that it's better if we pass all of the rights to derive data through a data pipeline. And a data pipeline, in our case, is based on Kafka. But the way it works is that we take writes to our sources of truth from logic. So things like MySQL tables, Kafka, or Zookeeper. They take writes from the application. But then we hook into the write streams from those data stores, and we're able to denormalize it into any data store we want. So for example, if we have 15 different Elasticsearch indices that we need to update when a user checks in, we can do that in the data pipeline. And we found this to be much more reliable than requiring the logic to do all of those keeping consistent of data. And we actually wrote a multi-part blog post on our engineering blog about how we do this, about how this actually works in production. It's a great series. I highly encourage you guys to read it. All right, but you've got the flip side problem too. You've got all the data coming in, but you've also got crazy read paths coming out. All your logic is reading data from everywhere. And this is really hard because, again, it makes it hard to change. When I want to move something from one Cassandra cluster to another, I have to go find all the logic that changes it. So what we found is better is to put a query proxy in between our derived data and our logic. And this has been really powerful because it makes it super easy to do things like upgrade versions of data stores. And that's because we've decoupled the APIs of the data store that we depend on with the APIs in the services and the logic. And I wrote this blog post a couple years ago about how we use this to, for example, do major version upgrades of data stores without dropping a single packet. I think this is a really cool technique. I think it's similar to the API gateway pattern that we've heard a little bit about at this conference, except for instead of between your presentation and logic, it's between your logic and your data. But you have to be very cognizant to not put business logic in this client, because otherwise it just becomes a monolith that's hard to maintain. So you do have to be careful when you're doing this. All right. So the next reality I want to hit on is this. How many of you guys have a separate DBA org? Yeah, a couple. We do too. I'll admit, we do too. But we found that it was better for distributed data if we brought the DBA knowledge in and had developers own their data. And even if they don't necessarily know all the intricacies of MySQL performance tuning or Cassandra performance tuning, just like we don't expect them to know all the intricacies of Linux performance tuning when they're deploying microservices, we do expect them to be responsible for their data store and for the data they're creating. I don't know, maybe we should coin like dev data ops, dev DBA ops, dev up. I'm not good with catchy names. We need a catchy name for this. But if you want to do this, your company is going to have to invest in it. Just like with microservices, you have to start educating your developers about operational things. You also have to do that with data stores. You're going to need docs, lectures, support channels. And at Yelp, my team, the platform team, does things like we have support IRC channels, we have weekly office hours, we have lectures that we record for developers, and we offer like one-on-one consulting sessions. Because hopefully our developers don't feel like this. Hopefully they don't feel like, oh, if only I had known, I would have written it right the first time. So we found this to be very important. As part of building that platform, you can't just build the tech, you have to also build the people and invest in the people. All right, so that's been, I hope, a fun talk. Some takeaways are you have a lot of choices in open source. And this is awesome, right? This is really exciting to me. But just because you have the choices doesn't mean that you should choose them all. When you do choose to go polyglot, make sure that it's for business reasons, not for Hacker News reasons. Third, when you do go polyglot, distribute your responsibility. Just like with microservices, your ops team can't be on call for all those services. With your data stores, your DBA team can't be on call for all these databases. Fourth, prepare for change. And these kind of came, I want to just reemphasize the idea of like that data pipeline and that query proxy. Because those little pieces, those little interfaces are what allow us to be able to change our derived data. And I think that that's really amazing. And finally, one size fits some. Don't snowflake functionality into a data store that isn't meant for it. Think about the trade-offs and understand the choices, and then pick the right data store for you. Thank you guys very much. And I think we have 1 minute for questions.
Go on, you can have one question if you want. Anybody want to ask a question?
Any questions? Yeah.
Hi, you mentioned that you put a gateway between your data and your logic, business logic.
Yeah.
So how do you maintain the availability of the data? And also the other side, you use only Kafka for writes, so you keep the Kafka to ensure that the data is actually good and you can pick it from the queues later?
Yeah. So two questions. The first question, if I understand it correctly, was how do you make sure that the query API, the query proxy is available? And the answer to that is that it's a stateless service because it doesn't actually have any state in it. It's pretty easy to keep that available. You just replicate it. It's like any other service in our infrastructure that has to be highly available. So we have multiple replicas across multiple multiple deployments, and because that API is just doing translation between the API the services speak and the API the data store speaks, there's no complexity in that proxy. It's pretty simple and relatively. Like I can say we've only had like one outage in 3 years because of it. So it's been pretty reliable. The second part of the question was, do you do all your writes to Kafka for the data pipeline, or do you write to other things? So we actually do most of our writes to MySQL, and then we hop off an RBR slave, so a row-based replication slave, and we actually parse the data that's coming out of MySQL in real time, and then schematize it and write it into Kafka. And that blog, the reason why that's a 5-series blog post is because this is a very complex topic. So that's why I didn't go into it here. But if you're interested, check out our blog.
All right, time's up. Thanks very much, Joey.
If you guys have any more questions, I'll take them in the back.